Hello students, today I am going to cover principal component analysis in continuation with the previous video of principal component analysis where I explained how principal component analysis resolves the problem of dimensionality and how it reduces the dimensions. So today I will calculate how to find this principal component with the help of an example. So let's start. Let us consider the feature vectors x and y with these 6 data points. And as the first step to calculate the principal component, we need to calculate the covariance of the matrix. So the formula for covariance matrix is this. We will calculate step by step as firstly we will evaluate this, then we will evaluate the summation of it, and then the whole covariance equation. So firstly, we calculate the x minus mu, where mu is the mean vector of the data points. So if I calculate the mean of these data points, so we can easily calculate the summation of x data points by 6 because I do have 6 data points, and this y I do have 6 data points, so summation of this divided by 6, so we do have this mean vector. Now in the second, I will calculate x minus mu. So I will calculate this 2 minus 4.5, 1 minus 5, 3 minus 4.5, 5 minus 5, 4 minus 4.5, 3 minus 5, 5 minus 4.5, 6, 5, and so on. And after solving this, I may get these values, right? Now I need to calculate the projection or multiplication of the matrix and its transpose. So here I calculate this minus 2.54 and its transpose, minus 1.50 and its transpose, minus 0.5 minus 2 and its transpose, and so on, right? And after solving this, I may have these matrices. Now I need to calculate the summation of these two, the matrix and its transpose. So what I need to calculate the summation of all the matrices which we have calculated earlier. So the summation of this is this matrix 17.5, 18.5, 18.5 and 28. Now I need to calculate the covariance of this matrix. So I need, as n is the number of data points, which is 6 over here. So I have divided 6 with this matrix, and the resultant one is 2.92, 3.08, 3.08 and 4.67. Now I have to calculate in the second step as eigenvector. So for calculating eigenvector, we have the formula Ax is equal to lambda x, where we put the value of the matrix A over here. So after putting the value which we have calculating from there as the covariance matrix, so I put this covariance matrix over here, and the equation is now in this way. Now after solving this, the determinant I got, that is 2.92 minus lambda, 3.08, 3.08 and 4.67 minus lambda. So we have the equation by this determinant as 2.92 minus lambda, 4.67 minus lambda minus 3.08 ka whole square, where I get this equation. So now it is a quadratic equation, and you know how to calculate the quadratic equation. That is the roots of the quadratic equation minus b plus minus underscore b square minus 4ac upon 2a. This is the general equation which we have remember since our childhood. So we calculate by this the lambda 1 and the lambda 2. So from this values, this is actually our eigenvectors. So as you know, lambda 2, that is 0.51, is greater than lambda 1. So we consider lambda 2 as my first eigenvector, which I already explained in the process of calculating principal component, that the highest or the largest the eigenvector would be my first principal component. So I get my first eigenvector. So I need to put this eigenvector into the formula. So lambda 2 is my first eigenvector. So as lambda 1 would be my second eigenvector. So I need to put the values of lambda 2 over here. So I kept lambda 2 in this place. Now I need to resolve this equation. So after simplifying this equation, we get these two equations where we do have two unknown values x and y. After simplify these two equations, we do have two equations where first equation tells that x is equal to 1.35y and x is equal to 1.28y. We may consider any one of the equation for our principal component purpose. Now we need to plot this into my xy data points. So firstly, the data points which we have taken earlier, we need to plot these data points. So to project these data points into the feature space, we have projected those 6 data points in the feature space. And as the equation we get from simplifying the eigenvector and eigenvalue, I will calculate I will put all the values of y and get the values of x. So I randomly take some continuous numbers 0, 1, 2, 3, and with respect to these y values, we get the value of the x. Now I put all these x and y value in this feature space graph. So you can easily see that we have created our first principal component with the help of those steps, and we called it as first principal component. In the same manner, with the help of the second eigenvector, we can calculate the second principal component. The steps would be the same as we have gone through the steps of calculation. So this is actually how to calculate the first principal component and the second principal component. This is the theory part of PCA. You can easily get it through from my notes also, which I have already sent to you. The steps which actually we need to go through while calculating the principal components. Now there are some disadvantages which we are facing while doing dimensional reduction with the help of PCA. Firstly, one of the important limitation is the calculation of covariance matrix, which is very difficult because as the data points will get increased, it will be very difficult, or the computation power would be very high. The second disadvantage is the simplest invariance cannot be captured by the PCA. So the training data explicitly, if provides the solution, then only we can capture the PCA values. The third is PCA always consider the low variance components in the data as noise and recommend throwing among these components. So actually PCA consider only the low variance component, because when I see the variances which is in a single direction, so PCA will consider the low variance vectors. So this is also one of the disadvantage, and these low variance to components which actually PCA considers may have the noise and the distortion. The next one, PCA does not tell which feature of the cell data set would be most significant, as PCA only creates the principal component, and considering the data points which has been projected on that principal component, but principal component analysis may not actually represent the important features of any data. And the last limitation is PCA assumes that the principal components will lie on the orthogonal or on the diagonal of any feature space. So these are the disadvantages of principal component analysis. I hope principal component analysis would be clear to you after watching this video. Thank you, students. Keep watching and listening.